Have you ever wondered what is the molecular basis of the sensation of touch? In 2021, the Nobel Prize in Physiology was awarded to Artem Patapoutian for discovering a protein that can sense mechanical force. This protein is Piezo1, a protein that acts like your body's biological pressure sensor. Piezo1 is a mechanosensitive ion channel, meaning it opens in response to mechanical stress. It's located in the cell membranes of many different tissues, like the lungs, bladder, and skin, and even in red blood cells, where it helps regulate cell volume in response to hydration. When force is applied to the cell membrane, Piezo1 opens to allow positively charged ions like calcium and sodium to flow into the cell, triggering downstream responses. A specific mutation in this protein is linked to hereditary xerocytosis, a rare form of hemolytic anemia. Structurally, Piezo1 is shaped like a three-bladed fan, and this unique architecture plays a key role in how it senses mechanical forces. The curved blades sit across the cell membrane, and when tension or pressure is applied, either by stretching, compression, or other mechanical stresses, the blades flatten out, like a spring in coiling. This structural change is what pulls open the central ion channel, allowing cations like calcium and sodium to rush in. Piezo1 is also homotrimeric, meaning it's made up of 3 identical subunits. Each one includes 1. A peripheral blade, which senses and transmits mechanical force, 2. A beam domain, which acts like a lever to relay that force inward, 3. A central pore where the 3 subunits meet and ions flow through, and 4. Anchor and cap domains, which help stabilize the whole structure. In my model, I represented the fan blades, the beam, and the central pore where the subunits come together. Some of the internal domains are less visible, but the model captures a major architecture. It also shows both tertiary and quaternary structure. The tertiary structure refers to how each of the individual polypeptides fold into the entire 3D shape, and the quaternary structure is how all 3 folded subunits come together to form the full protein complex. You can take the model apart to see one subunit on its own, or assemble it to see the complete channel. So, how does Piezo1 behave in the cell? Well, in its resting state, the channel is closed with the blades curved upward. When mechanical force is applied to the membrane, the blades flatten, and the ion channel opens briefly to allow a burst of calcium and sodium ions to enter. There's a key site near the pore where a positively charged arginine helps stabilize the closed state of the channel. In my model, I used magnets to represent this electrostatic interaction. When the R2456H mutation occurs, the arginine is replaced with a histidine, which carries less charge. So if you remove one of the magnets in the model, you can see how the channel becomes easier to pull open. And in the real protein, this means the channel can stay open for longer than it should, letting more ions flow into the cell. In red blood cells, this triggers a cascade. The excess calcium activates the Gardose channel, allowing potassium to now leave the cell. Chloride follows to maintain charge balance, and since solutes are now outside the cell, water will follow and leave too, resulting in a dehydrated, rigid, red blood cell. These cells can't squeeze through small blood vessels properly anymore and are removed by the spleen, leading to hereditary xerocytosis, which is a type of chronic hemolytic anemia. Like any model, mine definitely has some limitations. First of all, it's static, while real proteins are more flexible and dynamic. Secondly, it doesn't show the membrane environment Piezo1 exists within, which is really essential to understanding Piezo1's function. And thirdly, it doesn't include any post-translational modifications like glycosylation or phosphorylation that might affect how the protein behaves. And finally, even this explanation can be a bit of a simplification. Piezo1 is a relatively new discovery, and researchers are still figuring out how it really works in living cells. There's still a lot we don't know, and new discoveries are being made all the time.